Hi, so here's another one I've figured out. This is orbital motion, and it's all done in geometry nodes. So let me give you a little bit of the theory. You can look this up online. It's in like any orbital mechanics books. God, this stuff dates all the way back to, Kepler, so quite a while ago. This is orbital mechanics, and all I'm doing here is using the equations for a stable orbit. And so there's eccentricity of the orbit, it's assumed elliptical. There's delta t, which is a time increment. And the thing about this is that for an elliptical orbit, equal areas are swept out in equal times. So you can use that as sort of, it's not like Euler integration that I have in another video, but it's a way of calculating a change in position due to a change in time, because the area because of the equations for an ellipse, and you have a delta t that's determined. You have some angular momentum, and this is all derived from the general equation of like two bodies. So you have the gravitational constant times the mass of each divided by the distance between them as parameters in the equation. And again, you can just look this up online. Maybe I'll put something out there that has a little more details on the derivation. I did that for the single degree of freedom oscillator that I did before, and I don't think too many people are looking at it, so I don't know if I'll do it for this. So there's an angle, a radial vector distance. The ellipse has two focal points, and then the radial vector, that distance, is from one of those focal points, which is the location of the heavier object, and then r is the distance from that heavier object to the small object that's orbiting around it. So here I'm saying, okay, let's start with delta t. Let's make it 1 over 24, since we have 24 increments per second in Blender. And then the equations, again, you can look this up. dA equals dt over 2 times h, which is the angular momentum. And then equal areas are swept out in equal times. That goes back to Kepler. I'm assuming that angle is 0 at time equals 0. And then the delta nu, which is the, sorry I wrote v there, but that's the v naught equals 0. It's 2 over that distance times the change in area. And this is the equation for what that distance is. It's p over 1 minus e, which is the eccentricity, times cosine v. So that's basically it. All you have to do is implement this with the ping-pong method, and I'll put the link to where I found that method. And if you look at some of my other videos, I'm playing around with time integration using that method as well. This is a little simpler, actually a lot simpler, but it's the same sort of thing. So you have a ping and a pong. And the ping is where you're doing all your calculations, and the output of that goes into the pong object. They're both geometry nodes. And the pong just feeds through variables that you're calculating back into the ping. So here I'm showing you, say that's the sun at one of the focal points of the ellipse. That's a planet going around it. And then the angle starts at 0 there. And then you have an angle swept out to a new point, which is r. And that's like a new location of that planet as it rotates around. So when I'm calculating it, I'm getting a x location and a y location. So that's our cosine nu and our sine nu. And then that feeds into a set position. For here I'm using an icosphere that's shaded smooth, and then you just let the magic happen. So now let's see what's in this. So here's my ping. It's not that bad. And here's the pong. The pong is pretty simple. So the pong, I just dragged the ping object into it. You can see over there on the right that the object is ping. And then I have three variables that are fed through nu, which is the angle, and then r cosine nu and r sine nu, which are the positions. And those are just fed through each iteration when you're running a simulation. The ping has more to it, but the object in there is the pong, and I'm using an icosphere. I did a subdivision surface and then a shade smooth. Here I'm saying that at frame 1, that icosphere is going to become the geometry, and then after that, it's whatever's in that pong object. And here on the right, you can see the ping reads in the pong object, and then there's nu cosine, our cosine nu and our sine nu as the inputs, and the outputs I have a couple more, and up above you can see that those are just things that I wanted to output as I was troubleshooting this, and it goes out into the spreadsheet if you look at that. So the nu is I'm calculating the delta nu and adding the old nu, and that goes into a capture attribute, and that goes into the output there. The r cosine nu and r sine nu go into a combined xyz. They're subtracted from the positions that I'm plotting, and then that goes into the offset. So that's how I'm calculating each incremental change in those positions, because the offset is expecting that rather than the absolute locations at each time. So that's nu, and this is r, and that's where I'm calculating r cosine nu and r sine nu. And down here, nu is coming out of this. At time 0, I'm saying that that's going to be equal to nu naught, which is 0. And then that goes into a cosine multiplied by e, so then you get e cosine nu. You add 1 to it, and then take p and divide by that quantity, and then you get the equation that we had for r, which is p 1. Sorry, I realize now that I'm recording my voice that I wrote down minus p, but it's 1 minus e cosine nu, but it's plus. So dA is delta t divided by 2 times the angular momentum. And then once I have dA, I can go ahead and calculate delta nu, which is 2 divided by r squared times dA. So here I'm taking r, that's where I got r, take it to the power of 2, and then that goes into a division where I've already calculated 2 times dA. So then you get 2 times dA divided by r squared. And that's delta nu, that gets added to the nu from the switch, and then that goes into a capture attribute and then into the output. And here, that's where I'm getting the R cosine nu and R sine nu. And they're both going into capture attributes as well and going into the output. I had a couple more capture attributes in there, but those really aren't important because those are things I was using for troubleshooting. But that's another way you can get some of the information from the system that you're creating and make sure your calculations are coming out right. So here at time equal frame 1, we're setting the geometry to this icosphere with the shade smooth and all that. And then every other time, it's just whatever is fed in from the object. And really, that's it. I made two different, I made a copy of the system and I changed some of the parameters. So here you can see the H is a little different, the E is a little different, and the P is a little different. And that's how I got the one in the middle that has almost no eccentricity. And then the other one is a little more eccentric. It's 0.6 for the eccentricity. It's a little more energetic. The angular momentum is higher. And then the P is a little different. And you can just play around with the parameters and get something that you like. So really, that's about it. I hope you enjoy this and have some fun playing around with it. If you have any questions, shoot a comment. And please like or subscribe. All right. Have a good one. Bye.